Good morning, and welcome to Westfield State University. We're delighted that you're here in our campus. Westfield State University was the first public institution to host this conference in 2006. And we are thrilled that we are back on our campus. I wanted to thank Dr. Johnson and also Skidmore College, Dr. Vila, for your efforts in organizing this terrific day for our students. Thank you for the math department, the faculty of the math department. You're second to none. And I wanted to welcome and congratulate the students presenting at this conference. Now, I hope that you're going to stroll on our campus, and those of you that perhaps were here in 2006, you're going to see that our campus looks a little bit different. And I'm pleased to tell you that on May 5th, we are going to be dedicating our Science and Innovation Center. The Science and Innovation Center will carry the name of a distinguished alumna, Dr. Natty Maria Stevens. Her work, her research changed society, changed our understanding of human development. Briefly, Dr. Stevens discovered the XY chromosomes. She is a role model for all of us. We're proud of her work, but she's especially a role model for women in the sciences. Now, as I look around the room, I'm very envious of your passion and your love for mathematics. I came to appreciate and respect and even like mathematics later on in graduate school. You see, when I was an undergrad, I did not know what to do with math. Nobody told me why I was taking algebra. Really, I couldn't make sense of that. Why should I? But in graduate school, I learned that math could tell a story, could inform social policy, could impact social change. You see, I discovered that math was not static. I was interested in the study of poverty. And back then in the 70s, poverty studies was fairly static. Everything was reduced to a regression equation. You had your coefficients, and you were trying to predict your independent variable, your y. That didn't make sense to me because time is important in the study of poverty. If you are in poverty for 2 years, the probability of moving out of poverty is different than if you were in poverty for 10 years. And so it was math. It was Cox model and hazard model that allowed me to introduce time as a variable in the equation in the study of poverty. And so I was able then to tell a story of rural poverty in the United States. So it gives me great joy to see all of you here engaged in your studies of mathematics and your research in math. This is the cornerstone of your undergraduate studies. And this is very much aligned with Westfield State University and what education at Westfield State University represents. I'm proud that we are making an investment in student research, and I'm very proud that we are funding the Center for Undergraduate Research and Creative Activities. I wish you a productive, engaging, challenging, and fun conference. Congratulations and welcome. Thank you.
To introduce our keynote speaker will be Lauren Zanes. She is the winner of the Mathematics Department's Academic Excellence Award, along with Nathan Pickett. She is a wonderfully dedicated student and is currently doing her student teaching for licensure to teach mathematics here in Massachusetts, and I know she'll work hard to pass on the beauty of mathematics to her students in the years to come. Please welcome Lauren.
Hello, I'm Lauren, and today I have the honor of presenting our keynote speaker, Professor Noam Elkies. He is a man that has lived a remarkable life, and his knack for success began in his adolescence. At the young age of 15, he graduated high school and moved on to an undergraduate career at Columbia University and studied mathematics and music. At 18 years old, he graduated as a valedictorian of his class. And then at age 20, he moved on to earn his PhD at Harvard University, where he studied under Benedict Gross and Barry Mazur. To add to his numerous successes, at age 26 years old, he became the youngest full-tenured professor at Harvard University in Harvard's history. Now, most of Elkies' work surrounded number theory, and he is responsible for many findings in the field. For a handful of examples, he proved that an elliptic curve over the rational numbers is supersingular at infinitely many primes. He also found the first counterexample to Euler's sum of the powers conjecture for fourth powers. Lastly, he and A.O.L. Atkin are known for their extension of Scoof's algorithm, which made the algorithm more efficient. Elkies is not one-dimensional, though. He has a broad range of interests outside of mathematics, including classical music and chess. In music, he composed several works, including a 7th Brandenburg Concerto, and in chess, not only did he earn his master title, but he also doubles as a composer of chess studies. So now, ladies and gentlemen, I would like to introduce to you now Professor Noam Elkies.
Very much. Can you hear me? Yeah. Thanks for this great introduction and for the organizer's kind invitation to join this now 24th HRUMC and giving me my also first opportunity to visit Westfield. Thanks in particular to the designer of this poster. I actually recognize the music. It's from one of the Mozart piano concertos, one of the only 2 out of the 20-some that are in minor. Sounds like... and so forth, but that's already outside of the stage. And when people hear about some parts of my interests, namely the fact that I have done work both in mathematics, which, let's see, I need to rotate this 3 times, I think, both in mathematics, working with integrals and such, and in music, I'm often asked what about connections between these 2 areas. There's, of course, plenty of anecdotal connections going all the way back to the Pythagoreans, and unfortunately also plenty of people trying to force connections or trying to draw connections that are, to be frank about, as don't go much deeper than this visual pun that I drew here. But there are a few cases, and I believe that the question that I'm going to be speaking about today, there are a few cases where having a mathematical point of view, if it does not completely solve the question coming from music, will at least give some new kind of insight about the question about what the kind of things we care about in music. So I introduced the question, I gave the title of Entropy of Music, Now, entropy in public discourse is, disorder. It's something undesirable. But it's a concept that comes to us from physics, and it's a key insight of physics that entropy, among other things, is a measure of information. That is to say, can you see this, or should I use a different pen? I can't hear. Okay. So, that is to say, if something is totally structured, if something has a completely regular pattern, it carries no information at all, because everything is predictable. Whereas if something seems disordered, it is the specifics of what appears where and when contain information and can carry data. And so information in turn is something that we study in mathematics and computer science, right? So this is basically a physics notion, this is a computer science notion, and this is related with the kind of questions that we study in combinatorics, which is a number of possibilities. So that's related to mathematics. And the key, and fortunately, because of computer evolution, we all have some sense of how we measure information. We measure information in, megabytes, kilobytes, bits per second, but the fundamental unit of information that we use, I have my notes here somewhere. I remember most of this, no? Oh, here it is. Okay. The key unit of information that we use is what's known as the bit, which is a useful mnemonic. Can you see that bit? No, you cannot. So, bit, as you may know already, is short for binary digit. It's a matter of personal preference whether you want to get the I from the binary or from the digit. But at any rate, it's a 0 or a 1. It's exactly the amount of information you need to encode a binary choice, 0 or 1, yes or no, true or false, black or white, from what we heard in the president's introduction, X or Y chromosome, etc. And so, once you are able to make one choice repeatedly, you can choose from as many things as you want. As we know from the game of 20 questions, I'm going to get there, but before we get to, so one bit we have 2 choices, and before we get all the way up to 20 and beyond that, 2 bits. Of course, if you have 2 bits, the first one can be either 0 or 1, and the second one can independently be 0 or 1. And so there are 4 choices. Numbers from 0 to 3 or from 1 to 4, equivalently, well not equivalently, but another familiar place where you have 4 choices is the letter of the genetic code. Letters of the genetic code, the chemists tell us, really do come in a 2x2 structure. There is, I'm not going to go into drawing chemical symbols and chemical diagrams in a math talk, but there are bigger ones and smaller ones, and they have each one has 2 different modifications, and they fit into each other to form DNA. And then for 3 bits, so we had 2 choices for 1, 4 choices for 2, so for 3 you should have 8. Because after all, having made 4 choices, we can append either a 0 or 1 to each one of them. 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. We are, of course, constructing the binary numbers, 0, 1, etc., up to 7, and you can distinguish any out of 8 choices. So for example, the choice of one of the 8 notes of a major scale is given by 3 bits. And the fact that there are 8 notes is ultimately the reason that we use, sorry, the fact that there are 8 notes is ultimately the reason that we use the word octave for the distance between them. It's originally the Latin word for the 8th of something, Latin or Italian, in the word of fifth. The 5th note, in other languages they actually say quinta, in like Hebrew that's actually the word for musical 5th, taken from Latin. And of course, that theory was developed before people started counting. Everybody's a critic. Before people used to count at 0, and so if you add 2 musical 5ths, you end up with a musical not 10th, but a 9th, and that's because the 5ths overlap. And while I should have really started to count at 0, an interval of 4, 5, 6, 7, 8, and then 4 plus 4 equals 8, but that's a different talk, and I'm not going to go further into musical intervals here. You can probably guess at least what the next number in this sequence is going to be. You have 16 choices for 16 bits. In general, it's going to be n bits giving you n choices. And that is, of course, the binary numbers from 0 to 15, or the hexadecimal digits. And once you have 16 of them, you can encode an ordinary digit. You need at least 4 bits. You need these 4 bits to encode a single decimal digit, because if you have only 3, there are 8 possibilities. And by Cleveland principle, there will be some of the 10 digits that get encoded by the same thing. And so you might have seen this already as BCD, binary coded decimal. So binary coded decimal. And of course, you can encode anything that has 16 or any other object of which you have 16 or fewer possibilities, like the 12 possible notes within an octave, what musicians call the 12 pitch classes. So G is a pitch class, it's the same pitch class as this one. And G sharp or A flat is another pitch class, and there are 12 of them. The reason that we have 12 and not some other number is yet another topic for different math and music talks I'm not giving today. And just to go a bit further, by the time you get up to 32, you have enough possibilities to encode the letter of the alphabet. Well, a letter at least of, let's say, the English alphabet. Then you have 26 choices, and so that lets you put in a few extra symbols, maybe the space, the single and double quote, and a few basic punctuation symbols. So that's 26 for 6. If you use the Hebrew alphabet, that has only 22 letters, and so you can actually encode a letter or a digit in 5 bits, and that was something that the Kabbalah scholars made a big deal out of. The Sefirot of Kabbalah are probably originally the same word that is now in modern Hebrew, Sfarot, which is just digits. They're just the digits from 0 to 9. You can make a universe out of the digits and the 22 letters. So basically, they're early experts in information theory. Just one more example before we skip. 64 choices. Well, you can group them in various ways. You can write 64 bits, 6 bits as 2 plus 2 plus 2, and that means that you have 4 times 4 times 4 choices. And that, of course, means you have triples of letters from the genetic code. And if you remember, we have more or less 20 amino acids that all of our proteins are built out of, and they are made out of, and they are encoded by these triplets, and they have to be triplets for the same reason as before. So just try to use two base pairs per amino acid. You could only distinguish 16 of them, and you actually need a bit more because you also need a special code for saying stop transcribing. Otherwise, you transcribe your entire DNA molecule into one huge protein. So, so that's 64, which is bigger than 20 plus one code symbol, one stop symbol, excuse me. Or you could split this up into 3 plus 3, and then you get the 64 squares of a chessboard. So a square on a chessboard is specified by 6 bits, and if you play computer chess, you're implicitly using this. Also, I mentioned already that the 8 bits are enough to encode a major, in a major note on a one octave major scale. 4 bits are enough to encode a note on a chromatic scale. Once you get up to 64 notes, you have almost enough bits to encode a note on the piano. And it used to be you had enough because at least through Mozart and early Beethoven, the piano didn't go all the way out to 88 notes. There were only, it went only down to this F and up 1, 2, 3, 4, 5 octaves to this one. And so there were a total of, if you remember, there are 12 notes to the octave. So 1, 13, 24, 37, 49, 61. So you could encode a note in any Bach, Mozart, early Beethoven piano piece by 6 bits. And then we can keep going for a bit longer. I'm not going to say anything special about so I'm not going to say anything special about 7 bits, but 8 bits is a famous unit. 8 bits you might know is called a byte, so that's 1 out of 256 possibilities. And so that's all of ASCII, for example. There are 256 possible ASCII symbols, including all the capital and lowercase letters and stamp punctuation and a few other things. And then 1024, excuse me, I'm on the wrong side. There are 1024 choices here, which is 10 bits. Now 1024 is noticeably close to 10 cubed. And 10 cubed, of course, is 1,000, what we sometimes call a kilo. And that's why in computer science applications, we use kilo as a prefix for 1024 because computers like to count in pairs. Now, you might remember I told you we cannot use as few as 3 bits to encode a digit. You need at least 4, but that's sort of waste information because or to waste entropy, if you like, because I have not, I have 6 possibilities I'm not using. So that was 4 bits per digit, but if I waited until I have 3 digits to encode, then I could have encoded them all together with a number from 1 to 1,000, which I can encode in 10 bits. And so that tells me that it actually takes at most 10/3 of a bit on average to encode 10/3 bits to encode a single decimal. And of course, what this is eventually approaching is the logarithm base 2 of 10. And the fact that 1024 is so close to 10 cubed accounts for the fact that log base 2 of 10 is so close to 10/3, or in a more familiar form, that log base 10 of 2 is so close to 3 tenths. In the old days, when we had handheld calculators, it was very easy to press 1 log, and of course you got nothing. You got 0, which you knew already. You press 0 log, and you got an error message. The next thing you got is 2 log, and you got this number 0.3010, almost 3. It was 299,957, etc. And this is very close to just 0.3. You say 3/10. And it's just a bit higher than that, because 1024 is just a bit higher than 10 cubed. So, I promised you 20 questions. If you give me 20 bits, that's already the square of 1024, which is therefore a bit over a million. So if you play 20 questions perfectly, then you can distinguish one out of a million objects. Except that it's a bit more than that, because there's a standard thing you're allowed to start with animal, vegetable, or mineral. And so that's 3 options, which should really be allowed. You could actually have not 20 bits, but 19 plus log base 2 of 3, whatever that is. It should really be called 20.5 something questions. And then going a bit further, of course, these exponentials build up quickly. Once you get up to 333 bits, that's enough to get just under 1.75 times 10 to the 100. So just say a Google is encoded in fewer than 333 bits, and then you keep going. 8192 is 8 times 1024, so that's so 1024, remember, is kilo, 8 is a byte, and so this is a kilobyte, and that's already 1 out of, 10 to the power 5, 6, 7, 8 as it happens choices, and then you keep on going. There's a megabyte, which is 8 million bits. And this used to be huge. Like back when I got my first programmable calculator, it had the equivalent of what we now think of as 2,000 kilobits, I think it was. That was huge. I could finally do programming and so forth in something handheld. And now that's that's a speck of what you have in your in your cell phone. And I'm not even going to write the number here, but of course it's roughly 10 to the power 1,000 times that. So a megabyte is enough to encode a huge amount of information, and in the sense of it's tries to distinguish between 1 in 10 to the power 5 million and some possibilities. And so how much of that kind of information do we need to encode a piece of music? As I mentioned earlier, that's more or less equivalent to the question of how many possible pieces of music are there, or what's the entropy of music, which is officially my clickbait title for this talk. Well, there are some problems here. The problem is that even if we have a well-defined way of measuring information or measuring the number of possibilities, we don't have a well-defined notion of music. So that's one problem. It's not even clear it's a well-defined question. Even if it were a well-defined question, it's not clear why you would study such a thing. I mean, it seems to be like the definition, and it's a key example of like purely curiosity-based research. Yeah, it's amusing to contemplate how many possible pieces of music there are, but who cares? And the answer is, well, as often happens in any kind of mathematics, be it pure or even applied mathematics, there are questions that seem to come to you, just out of curiosity. And if you think about it enough, you actually get some insight about the topic, in this case, what we mean by music, information, etc. That might not have been obvious to start with. So I'm claiming that this is going to be the case here. Now, what's music? Well, I mean, that's even hopeless to define in what's mathematics. I mean, it involves sound, but that's about all you can say about it. And it might not even involve sound, because they've seen people describe paintings in the same language that's used for music, this passage in a painting and so forth. And people describe poetry in terms of the music of the language, even though there are no musical sounds as such. I'm going to be mostly talking about Western concert music. Sorry, I mean, that's one of my native languages. It seems to be, at least in linguistics, if you understand one language really well, it gives you a huge head start in things that happen in other languages. Because after all, English might be very different from Inuit. I apologize, the language is not called Inuit, but I can't actually reproduce the sound. But there are still languages are used by human beings to communicate to other human beings with the same structures in our brain, and so the same kind of concerns that eventually lead to English eventually lead to Inuit or Turkic or Japanese or any of the other common languages we speak nowadays, as hard as it is to translate from one to the other. And I'm claiming that at least some of the ideas that we will run into by studying, music of Mozart, Bach, Beethoven, and other things that sound like it, even though they're not as good, will be more or less the same kind of things that will arise when we try to understand, be it raga or jazz or Japanese gakuku music, etc. So that's what I mean more or less by music. But there is, even once you have specified your domain, how many possible pieces of music there are, that presumes that you can tell when two pieces of music are the same or different. So you need to tell what it means for two pieces of music to be the same. So let me give a very, very simple example. Not even the whole piece, just those first 4 notes of Beethoven's Fifth Symphony. Everybody knows that. I mean, everybody has heard that tune, or that motif, whatever you want to call it. Even this little snippet, in some sense, has uncountably many possibilities. And so is somehow encoding not just infinitely much information, but uncountably much information. What do I mean by that? Well, what do they have to specify? Well, I played 4 notes. The same note 3 times, and the last note, and 1 note once. So you would think, I mentioned already, well, there are 5 bits to specify a note, so each one of these is specified by 5 bits, a total of 20 bits. But no, because that's not all there is to what I just did. After all, that doesn't sound like Beethoven's Fifth. That sort of sounds like a parody of the Fifth. Then there is. So there's already some, some parameters that you see. How long is each note? How loud is each note? When does each note start? Each one of these is a real variable. And we know there are uncountably many real numbers. So that might seem to suggest there is already uncountably many possibilities for, a single note, let alone the first 4 notes of Beethoven's Fifth, let alone the whole symphony. And there are a few other such continuous variables, like the tone quality. I'm playing this on piano, and actually played this. So each note was doubled at several octaves. But it's of course not written as a piano piece, although for many years before recordings, it was actually more common that you heard it played in piano arrangement than for orchestra. But even then, there are different pianos, they have different sounds. If I sing it, or play it on the violin or on the clarinet, each one of these has a different profile of sound, of tone quality, and tone qualities are parameterized by, Fourier spectrum or what have you. That's an uncountable set. Now, fortunately, there are various ways of getting around this problem. I mean, yes, we have some sense that it's sort of Beethoven's Fifth and isn't really. But there are lots and lots of things that count as Beethoven's Fifth, that is, they count as the same piece of music, even though they differ in those parameters, right? I mean, yes, if I played it 1% faster, if I played it 100 times faster, it wouldn't count as a symphony of Beethoven. If I played it 100 times slower. But if I played it 1% faster, instead of I went, you might not even tell that it's 1% faster. I know, maybe it's 3%. But you can't really tell the difference, right? I mean, that line of thinking eventually goes to what you might have already encountered in point set topology or metric topology in terms of neighborhoods and finite subcovers and compact spaces. The thing is that we cannot perceive a real number. We can perceive, a fuzzy neighborhood of a real number, and two performances that fall within the same neighborhood, we can't really tell a difference between them. So there's only going to be a finite number of possibilities. Well, you might say the real number is still infinitely long, and I could have taken a quarter of a second or half a second or 1 second, etc. for each one of these, but you're not going to stick around for a 1-hour performance of the first one all the way to the fifth. So that doesn't count. And even if you're willing to stick around for it, if I go too far, none of this is going to be around because we're not immortal. So there's only so these are only apparent infinities. There are other variations they could have taken. I mean, what is this? That's in some sense not the right piece because I played it in a different key. I played in C sharp here instead of C minor, which is what we wrote. But we have a sense that unless we are close to the best absolute pitch, that is the same music, just started in a different note. In fact, Beethoven didn't hear that. Most likely he heard something about a half step below that. That's another one of these infinite, apparently infinite, uncountably infinite ranges, which is actually in practice finite, right? Because I could have started half of the quarter tone lower or higher. And Mozart is said to have actually recognized that his violin at home was the 20th of a semitone below or above what he was playing in another city. But even Mozart couldn't tell it was a 1,000th of a semitone, and even for Mozart, fine, I'm playing an 8th of a tone lower, but it's still the same music. If I played this, that would be a parody of the fifth, but a piece within a certain range, it's the same thing. So, again, you can't actually give an answer to when two pieces of music are the same, because when two people consider the same performance or the same piece to be the same thing depends on your training and on your physical perception abilities and various other things. And there is the obvious problem, which is if I imagine, so here's one performance, here's another one. At one point along this line have I stopped moving from one to the other, right? I mean, it can't be quite an equivalent relation, because then finding any steps I'd show that those two are the same. So it's not really even an equivalence relation, but it's close to one. Again, I mean, this is using mathematical ideas and terminology to talk about things where that isn't an exact fit. So it's an approximation to what we are trying to measure, and we hope that we'll get some sense of the kind of information called in music, even if we cannot give literal definitions of everything. So I would, as far as I'm concerned, basically, the kind of equivalence classes that we'll consider more or less what's given by the musical score. So two different performances that we will, most musicians would consider to be renditions of the same music, will count as the same piece of music. And so, in some sense, I'm actually counting the number of objects of this kind. This is going to be our test case. It's the fifth prelude from the Well-Tempered Clavier, standard piece by Bach. It was such a standard that Beethoven, when he was 18, supposedly had already memorized each one of these pieces and knew them so well, there are 48 of them, each one of them so well that he could play them in any key, right? So I just play these 4 notes, one step higher. He could do the same thing with each one of these in any key you wanted. And even this is not quite right. I mean, because there are various editions of this music, and some of them actually differ in details that we consider to change the piece a bit. Others don't, because if you look closely, you'll see that there are various things here that aren't just the notes. I mean, there are things like this marking which says crescendo, get louder. That is part of the music, but Bach didn't put it there. That's an editor's marking. And then there are these numbers. Yeah, they're actual numbers, 1, 5, 1, 5, 2, 1, 3. That just hints to the pianist which finger you probably want to use to play the piece. If you decide to, you don't want to pay to your first page, you want to pay to your fourth, that doesn't change the piece, yeah? But we're basically counting how many such objects there are. So, how much time do I have, by the way? I'm going to get back to regular. How much time do I have? Anybody? 30 minutes, okay. So, enough to indicate what this piece sounds like, and then we'll try to figure out how much information is encoded when, and therefore how much information I had to memorize to do this. Hopefully I do more or less right. Maybe I should turn this upside down so I can't cheat by looking at the score. It's a graph where time goes, time is what's the word? It's the independent variable, the dependent variable is pitch. So this means go down, and then go up, it's the overs that count. Everything else is code that tells you like how long each one of them lasts. But it's basically, then all of these things happen at once, so in theory, but there is a long-standing convention that you actually do that. And so there are 2 pages, and there are 200 dots per inch scans. And so that suggests that we know exactly how to figure this out, because we have spent at rather possibly extensive, not excessive detail. We spent the first part of the lecture just counting bits. So how many bits are there here? Where there are 2 8.5 by 11 sheets, I'm just going to worry about orders of magnitude here. So 8.5 times 2 is 17, 17 times 11, 287. It's roughly 2 to the 8. 17 is 187, but it's roughly 2 to the 8, excuse me. And then it is 200 dots per inch, but this is inches squared, so 200 squared, and that's 40,000, which is roughly 2 to the 15th. And we have 2 to the 15th times 2 to the 8 is 2 to the 23rd, and this is a black and white scan, so each dot is either white or black, remember, either 1 or 0, so it's a bit. So there are 2 to the 23rd bits. That's why I stopped at 2 to the 23rd there, which is 2 to the 20 bytes, so it is 1 megabyte. So you might think, wow, I just memorized 1 megabyte of information. Just for reference's sake, remember a digit is 10/3 of a byte, of a bit. So it is, well, considerably less than a byte, and nobody has memorized a million digits of pi. Your phone number is 7 digits, so it's about 23 bits, so it's 3 bytes. But of course, I haven't actually memorized a megabyte of information, nowhere near that. This file is in fact 50K, 50 kilobytes. So it's already a factor of 20 less, and the reason is it's compressed. It's compressed because it's not just, a bunch of independent bits of information. There is this whole few lines at the beginning, ignoring this, which is my annotations of it, which are just all white, all zeros. So of course nobody's going to fill a table with zeros, at least not until they send it off to the printer to print it, maybe not even then. You're just going to have some code that says, oh, the next line is just, full of zeros. And that's, however long that code is, that's less than the 8.5 times 200, which is about 1,700 bits that you need to encode the first blank line. And likewise, second line, in fact, there's probably some code that says, you know what, the first H or so is all white. So you don't have to encode that. Even once you get to some information, you see there's lots of lines here. So if I had this perfectly aligned, you would have a whole line of just ones and then a bit of zeros at the end. So that's another thing you can encode. And you notice I'm just encoding almost one line at a time. And in fact, you can actually do a bit better by saying, well, this line is more or less like that line, except that some of the whites have changed to blacks, etc. And so there's a whole technology for how to encode, for how to compress information so that we're not wasting bits on just saying 0, 0, 0, 0, 0, 0. So that's one reason that this is less than the correct amount than the megabyte was a huge overestimate. And of course, some of the information you remember I don't need, like this 5 here, that tells me play this with the fifth finger. Well, thanks, I could have figured this out, and if I couldn't, it really wasn't part of the piece it wasn't part of what I had to memorize to do this. And so it's probably considerably less. Now, I already hinted earlier when I suggested that this sounds like it was only 20 bits of information, how many, one kind of way of guessing how much is happening here. And there's the whole matter of the rhythm, and you might have noticed that this is a very regular kind of music in some sense. So it's split up into bars of 4 quarters, 16th notes, again, this minor revision. And each one, at least in some sense, looks the same. The left hand always plays 4 notes, each half a beat long, followed by a rest. This is the symbol for rest. You see each measure has one of those, the only change is what the notes are. And likewise, the right hand, except for the initial note, is just playing a sequence of notes in the same continuing rhythm, so-called perpetual mobile piece. And the pattern breaks only towards the end, where he starts doing, well, at first he said, okay, I'm going to, having reached this point to left hand, yeah, I'm going to keep doing this, but hold on to that A. And then the left hand gets into the action, it's more of just going oompa, 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 and so it eventually it's placed together in the right hand, and then there's some other thing that happens towards the end. But for the first 28 bars, it really just is that. And so that seems to make it particularly easy for us to count how many such pieces there could be, and therefore, how many bits are encoded here. Oops. That's not what I meant to bring up. Here it is, sorry. Right, so there are 28 bars. Each one has 4 notes in the left hand. I mean, there's a bit of prelude at the beginning where I tell you this or that kind of piece, but that's going to take a lot fewer bits to say than the actual amount of information. So there's 28 bars, each one has 4 notes on the left and 60 notes on the right, and I just told you it takes 5 bits to encode a note on Bach's keyboard, so times 5 That nicely comes out to 100. So only about 2,800 bits. Oh, that's way less than 5,000, than 55,000 bytes, which was about 200,000. So this is really all I had to remember to to memorize the main part of this piece. And even that's an overestimate. 28,000 bytes, 2,800 bytes is actually non-trivial. Remember, if your phone number takes about 23 bytes, so I'd have to memorize 100 phone numbers. But you see, there is structure here, right? So there's various kinds of structure. So I was referring before to the identification of information with entropy. But there's context for this information, right? So, I'm sorry, I have too many pages floating around, and now I can't find the one that I wanted to go back to. So instead of going back to it, let me just start a new one and say, well, we had a question of context. So the information is not flowing out there in free space. It's information that's new for the context. So for example, I mean, there's context that's just internal to the structure. Like, probably if the next node were not this, you'd be somewhat surprised, right? So that had a lot of information. Of course, there's several nodes, but even that had a lot of information. That last node had way more information than this would, because the beginning of this implied that. And that's almost just a structure matter. Even that's a bit cheating, because unless you see the template on the white nodes, you might not have reason to think I didn't mean that. Of course, it sounds strange, but that's because we have a context of Western music in the background. Or to give an even more specific example, this has very little content, but has more has very information content, because it's already implied by this not by anything structural, but just because we have heard, shaving a haircut so many times, and therefore if I did. The first time I would deviate from shaving a haircut, given the information that you have already from classical and popular music, that encoded way more information than any other note I could just play. So there is some implicit context here, but going into exactly what constitutes this context is fairly far than I want to go here, but you can already see some parts of it just looking at the score and or listening to what I played. So there are patterns here beyond just the fact that the left hand is always playing 4 notes, the right hand is always playing 16 notes. You notice that it's grouped into 4. It's grouped into 4s not just because of that's the convention of the way we write music, but actually indicates structure. And the structure of each one of these 4 is almost the same. It's 2 notes and then 2 other notes that either go stepwise above or stepwise below the second note. And it always alternates. You always have 2 notes going up, and then 2 notes going down. 2 up, 2 down, 2 up, 2 down, 2 up. You need a bit of extra information here to know that it's not this. But that's just one additional bit of information. It's a sharp there that tells you that's the first time we heard the G sharp. So that one actually has quite a bit of information. But outside of that, once we have established a pattern, or told in advance of this kind of piece, in fact, the third and fourth notes out of each set of 4 contain essentially no information at all. So if you go back to my formula here, it's not 4 plus 16, it's basically 4 plus 8. So that cuts us down to 60, and that counts the total amount of information down to 1680. And you probably notice that there are other patterns here. Like, for example, So for example, if you went up here, I eventually reached so what I just the end of what I played is exactly the same as except down a whole step. So again, as with these changes from zeros to ones and from ones to zeros, I didn't have to remember all of this, all the 20 nodes here. All I have to remember is it's the same as I played before, but down a whole step. That might not actually save me all that many bits, but it's easier for us as humans to remember because it's structured. And even more so, when I got to the second page, sorry. This already sounds very familiar. Because those 5 bars, starting from the third one there, it says fortepiano, that's again the editor's decision that he wants me to play this loud and then to go soft. But the reason he wants that is it's like a collection. It's something I've heard already. I heard it already at the beginning of the piece. It's exactly the same music, except again I've shifted it by, in this case, the interval fifth. So down 4 steps. Remember, we should have started counting at 0. So down 4 steps. And so instead of memorizing these, whatever I said it is, 100 bits that it took to, 100 bits, 500 bits that it took to encode these 1, 2, 3, 4, 5 measures, excuse me, 1, 2, 3, 4, 5 measures, all I have to say is, play the first 5 measures, but down 5th. That takes it out less. So you can keep doing that, and you find that in fact, the amount of information that you have, both because of structured things like this, and because of features of the musical universe that Bach is writing in, is not even as large as the 1,000 or so bits that I mentioned. I don't know an exact number for it, but it's in the order of a few hundreds. It takes some time to memorize it, but it's no worse certainly than memorizing a Shakespeare soliloquy, which everybody has. Not everybody, but every actor has done. Maybe everybody here has had to memorize to be or not to be for school. And again, the same kind of thing. It's not just the number of letters multiplied by the number of bits per letter, because there's structure. I mean, you didn't say to be or not to be. But that's not an English word. And even to be or not to be, again, it's the same 5 letters to T0 space BE as we just started with. So if you just repeat that. And so forth. So there's structure, and then eventually when you read enough words, they make sense, at least when you learn Shakespeare's language. And so you can remember it by the sense instead of by individual words. So so I haven't yet answered the question I started with. How much information is this actually encoding? I mean, if I keep going that way, you might think, this piece of music is so perfect, maybe Bach didn't have any choice at all. Maybe the amount of information is almost 0. Right? I mean, it sometimes seems that way. You try to write a new piece of music, and yeah, you can put notes on paper, but they don't make any sense. And how many examples do we have of music that does make sense? Well, I mean, probably the whole literature of music is well under 1 million pieces. Like Bach wrote 1,000, which is huge, and each one of them has several movements. But still, remember, 1,000 is 10 bits. So certainly less than 20 bits, which is 1 million. So to specify a good piece of music, all you have to do is specify one of these 1 million pieces that's 20. That's 20 bits of information. That seems too small. I mean, it might feel like this music is so tightly constructed and so intricately woven that if you pull apart one string, the whole thing will collapse. But it's not really that case, and I'm going to claim that in fact, if you work step music was quite as good as Bach, you can encode quite a few bits into every single piece, every single bar, and therefore that the total information content is still non-trivial. So by the way, before leaving this example, as an exercise, if you know the first queries from the same collection, try to imagine the same kind of analysis there. Right? I mean, it's the same kind of thing. It's regular motion. You see patterns within patterns within patterns. Like, you don't really have to know all 16 of these nodes. Because once you know the first 5, you know the others. And it's the same in every bar. Again, don't worry about the last, including coda, where it finally deviates from the pattern. And I haven't, and I didn't even mention that, yeah, there are 5 bits, but the left hand never leaves the bottom half, the right hand hardly ever leaves the top hand, so we save a bit there. Anyhow, so I have about 15 minutes left, I guess? Okay, good. So it's been claimed that every math talk should have, well, optionally at least one joke, but certainly at least one theorem. I haven't given you any theorems yet, but it's a bit hard to give honestly a theorem about something that is not as far from being mathematically defined as a good piece of music. But let me say maybe it's an alternative theorem. It's a theorem in quotes, which is that the number of, so I can have at least 1.5 bytes per measure. Per measure of what? Well, per measure of a piece of music, roughly like what you just heard. And so how am I going to prove that? Well, how am I going to outprove that, I should say? This is an out theorem. Well, I have to construct well, you might think I have to construct, well, if I'm going to have a piece that's, I don't know, maybe 60 bars, so 60 bars times 1.5 is 90, and remember, each byte is one of 8 possibilities, so you might think I have to construct 8 to the 90th pieces of music. Of course, I'm not going to do that. 8 to the 90th is huge, but what I can do is I have an algorithm where you give me 90 bytes, I construct a piece of music in a way that guarantees that any 2 different choices are going to produce 2 different pieces of music. Okay, now, actually have such an algorithm. It is not an algorithm that I can define mathematically because it involves, the musical training that I've had for ever many years. But I can tell you how the encoding works. And I can give you an example of that. So the theorem actually says, I said here, 1.5 bytes, which is 2 to the 12th possibilities. 2 to the 12th is 4,096. I'm actually going to allow myself 10 to the 4th possibilities per measure. Let's say I'm going to encode 4 digits. So you give me any random sequence of 240 digits, and I will eventually be able to construct a reasonably good piece of music where those digits are embedded so that you can recover them from the piece of music. And therefore, if you've given me another sequence of digits, I can tell the piece are different because at least one of the notes has to be different. And it's going to be the same kind of piece as, in some sense, as the boss would say, it's going to have measures that have the same general kind of structure. The right hand plays 60 notes in 4 groups of 4. The left hand goes boom, boom, break, boom, break, boom, break, boom, break in each bar. Left hand has a few more notes than that, but that's not going to encode information. The information is going to be encoded in the right hand, and it's going to be encoded 4 numbers between 0 and 9. And the way they're encoded is the second of each group of 4 encodes a note. So if you look closely here or anywhere else in this piece, the second note is always, so here it is this E, this F, G, F, G, I'm the wrong place. F, C, E, that's G, etc. Each one of them is just one of one of the white notes, even though the rest of it goes all around the place, and it's actually a much bigger range and allows some notes that aren't on the white key. So it's just the notes 1, 2, 3, 4, 5, 6, 7, 8. Of course, that's 8. I need 10, so I'm going to allow myself a 9th note. And I need the 0th note, 8, 7, 5, 4, 3, 2, 1, 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I'll take a random sequence of digits and encode this. How do you know it's a random sequence of digits? Maybe I just wrote the piece and then declared, oh, here was a random sequence of digits and I want to encode. Well, we have one more or less canonical sequence of random sequences of digits which people try to encode or commit to memory, and those are digits of pi. Unless you believe in some really, cockamamie musical mathematical conspiracy theory that the digits of pi have intrinsic musical structure. That's basically a sequence of Stoner-Foley random notes. And so I have to embed them in a piece of music in such a way that the piece of music still makes sense. Otherwise, people have used this to memorize pi, but it's just, a sequence of Stoner-Foley random notes. It's no easier to memorize the Stoner-Foley random numbers. Whereas by embedding them in a structure that admittedly carries even more than those 240 digits worth of information, but tells a story, that makes it easier for our minds to remember it. We don't remember by compressing information, we remember expanding it and telling stories about it. So this is a musical story that encodes the digits of pi. According to steganographic etude, maybe you could read it there, so I expand this a bit. Steganographic means stegano is the Greek root for hidden, and steganographic sorry, I'm zooming out instead of in. Steganographic refers to a way of encoding information in something like a GIF. GIF? I don't know. An image file, which remember consists of, so it's not just black and white, it is a color file, so each dot actually has 24 bits attached to it describing, red from 0 to 255, green, blue, so 8 red, 8 green, 8 blue bits for a total of 24, and every once in a while, if need be, I change the blue bit, let's say, from 0 to 1 or from 1 to 0 to encode the next bit of my message. And it looks just the same because we can't really tell if there's 253 or 252 bits of blue in the picture. So same kind of thing here, except I'm encoding it in music and a lot more densely than you usually do in steganography, because remember, it's essentially every fourth note in the right hand. And it actually serves as a mnemonic for pi. To say, by memorizing this piece, I've implicitly memorized the first 244 digits of pi. It'll take me a bit long to recite them all, because I have to basically imagine these 3, 2, 9. I might as well leave this up there still, so you can actually see how it works. This is the music notation. Oh, here it is. Right, so you can see how it works. It starts sort of like this last piece I mentioned earlier, in that there are 2 notes and then going down, and 2 notes and then going up. It diverges from that eventually, but still 3, 1, 4, 1, 5, 9, 2, 6. And if I might remember in my ear or in my finger memory what I've been doing, I can extract those digits and go on this funny, very deliberate rhythm: 3, 1, 4, 1, 5, 9, 2, 6, etc. And as I said, it tells a musical story. So I guess I'll finish this talk by telling you this story, and then you can ask questions, etc. So zoom out, and so I guess I've said theorem, I haven't yet said proof, and so the proof is what I'm going to be making.